Good afternoon. I'm Cami Abernathy, Dean of the Herbert Wertheim College of Engineering. Thank you for joining us today. We have an exciting presentation. We're thrilled to have Chris Malachowski here with us today to discuss how the GPU changed the world. Chris co-founded Nvidia in 1993 and has more than 30 years of industry experience. He has been instrumental in managing, defining, and driving the company's core technologies as it has grown from a startup to the global leader in visual and parallel computing. As an executive at Nvidia, he has led numerous functions, including IT, operations, and all facets of the company's product engineering. Most recently, he was responsible for Nvidia's world-class research organization, which is tasked with developing the strategic technologies that will help drive the company's future growth and success. Prior to Nvidia, Chris held engineering and technical leadership positions at HP and Sun Microsystems. A recognized authority on integrated circuit design and methodology, he's been awarded almost 40 patents. He holds a Bachelor of Science in Electrical Engineering degree from the University of Florida and a Master's of Science in Computer Science degree from the Santa Clara University. Both schools have honored Chris with distinguished alumnus awards. Chris has served on the boards of the Computer History Museum and Hiller Aviation Museum in Silicon Valley and the Los Angeles County Museum of Art's Art and Technology Lab. He currently serves on the Herbert Wertheim College of Engineering West Coast Advisory Board. And as if all that wasn't enough, Chris has also received an Emmy for a film he helped produce that won Best Documentary in 2009. With that, I will turn the session over to Chris Malachowski to begin the presentation. Chris?
Hey, good morning, everybody. And before I get started, thank you, Dean Abernathy, for the introduction and the invite. So when I got the topic area, I thought I would just sort of run down memory lane and give everybody a snapshot of how we went from graphics to one of the premier players in AI. It turned out, though, as I dug into it, it actually caught my own interest in that even though I was involved in it, I never really stepped back to see where the critical junctures were that helped us make the leap from PC graphics to AI. And I thought I would share with you today how as I dug into this, how I put the story together, not just the story that you would see from 20,000 feet, I guess. And as I go through this, just keep in mind that AI is really just a moniker for all the machine learning and data analytic capabilities that has energized just a wave of innovation in the computer sciences industry and the world at large. And I also want to be clear that NVIDIA is by no means the first or only infrastructure and technology provider for AI, nor are we the only ones who leveraged graphics background to play in this arena. I do think we have a scale of focus and breadth and depth that is unique to us and differentiated. NVIDIA has also played a meaningful role in the development and the deployment of AI into the ranks of scientists and researchers and all sorts of products and services. However, especially in relation to AI, we stood on and are standing on the shoulders of giants. We like to say we're empowering the Da Vinci's and Einsteins of our time as a way of acknowledging those shoulders. I also want to say I'm going to, sort of do this in layman's terms, and I'm not going to try to be overly technically accurate if it doesn't help understanding. So my apology if I offend anybody in the liberties I take. Okay, with that, let's get going. So this is where we started. We started off trying to provide computer graphics in a multimedia way. Our first product, we teamed with Sega on the left. What I see on the left, the Virtua Fighter, was a game we were trying to bring to the PC, and we included wavetable audio and digital game controller as a way of trying to make a game console for on a card on the PC. The game on the right was just a sort of characteristic driving game. Both these games probably had a few hundred polygons, and the chip we provided for it initially was, I think, like 250,000 transistors. But one of the things that we did as a company is we never actually we were a chip company, but we always provided the software. We always intended to provide all the software to make our chip do what it did. And that turned out to be kind of unique in the industry. Most people provided an ingredient, the people you sold your chips to provided the software. We aspired to be a platform provider, like a game console, where you provide all the stuff and application writers right on top of it. That perspective, that desire to be more than an ingredient in somebody else's product, will play in this talk. So as I thought about the talk, there was lots of ways I could approach this. I told you how I ended up deciding that I was going to try to pick out the key spots in my own mind. But we started off being a better VGA device, if people remember VGA. And now we're the world's most prolific parallel processor with tens of millions of compatible devices of all performance levels, out in the wild. We were a component for consumer PCs, and now we're in the most expensive and most performant supercomputers in the world. We started off implementing a set of fixed functions, and now we're, overly programmable. Maybe not overly, but uh, you know, our programmability is what's helped usher in this new era. Um, we implemented, the way computer graphics was traditionally implemented was a pipeline, a series of stages of fixed function blocks that implemented an algorithm. And now we're a programmable engine that implements those stages. So it's no longer individual stages; it's a reusable part of the chip. Um, and as I'll show you, and I'll tell you in a few minutes, one of the things that happened is, enterprising graduate students, as it turned out, figured out how to use the graphics hardware to do general purpose calculations. And now, and you'll see they had to do headstands to do it. But now the computational engines that we've built our chips around also do the graphics. So there's sort of a flip there. And then the last one I thought was kind of cute because you know, we were trying, our quest and our evolution was to make better and better looking imagery. And the imagery was done in a way mostly to fake the human into believing it's what they'd expect, that it had all the right visual cues to be believable. And now, we're known for mimicking human intelligence in a different way. So I thought that was kind of cute. Um, but I think in the end, all of these are collectively tell the story, not any of them individually. So let me continue from here. Um, these are some of the things that go into modern computer graphics, whether they be capabilities or just the types of things you'd like to see in graphics. Most of these things historically, even though well understood physically, whatever the physical properties that would get you these things, their implementation in computer graphics were almost always a hack. It was always some mathematical games, some trickery that counted on the way the human's visual cortex worked, and we could fake the illusion of some of these things well enough that that the intent was to suspend the viewer in disbelief. But over time, you see this in Hollywood films and the CGI. You see there the trickery was getting better and better. Um, but to implement the actual physical phenomena or recreate the physical phenomena accurately was just too uh, um, computationally expensive. Hollywood could do it because they could run for months offline for a single frame. But in a game on your PC, this was not doable. So the trickery became the norm. Um, Let me also just use this as a point to point something out about computer graphics that I think will be relevant. Um, every pixel on the screen, your screen is divided into pixels, like a big 2D grid of pixels, 1 million, 2 million, 4 million-ish pixels. Each pixel has a color that's independent of the next pixel. Now, the thing you're trying to display may make the pixels related, but the individual color on a pixel is an individual calculation. And so you can envision calculating every pixel on the screen simultaneously if you could. So it turns out computer graphics is one of these, I always call it disgustingly parallel problems, applications. So the parallelism is known up front, and you choose based on whatever economics or complexity or whatever, when you're designing a chip to implement computer graphics, you decide whether you want to put out 1 pixel at a time, 2 pixels at a time, 64 pixels at a time, 256 pixels at a time, but you could calculate them all simultaneously. And that the nature of computer graphics, that its parallelism is known up front, turns out to be highly relevant in the story I'm going to hopefully lay out for you. Okay. So here's two diagrams. On the left is a typical characterization, generalization of a 3D pipeline. When I got into computer graphics, I was asked, I was a CPU guy. I designed CPUs prior, and I was given a set of mathematics and sketches of what I needed to implement in my chip at the time, to implement mostly 2D with a little bit of 3D graphics, but mostly 2D graphics. And as I started looking into it, I realized that all this mathematics was well known in advance. We were going to implement it, our differentiable opportunities were how fast we did it or how cheap we did it. As we got into 3D, again, all the mathematics and this pipeline, and the pipeline I'm referring to, the blocks on the left, the 3D to 2D transform, lighting, clipping, those blocks were implemented in series. So you had a block that would do the transform, you had a block that would do the lighting, a block that would do the clipping, and so forth. But all that mathematics was well known. It was captured in software that was readily available. You could read it in textbooks. And what I found, as I did sort of some competitive due diligence, is different companies would put more emphasis on lighting or clipping or texturing or any of these blocks, and they would put more emphasis here, the other company put more emphasis there, and one product would be better at something, another product would be better at something else. But the actual pipeline and what went into these blocks was pretty well understood. What the thing on the left evolved to was the thing on the right, where some of those stages where it was a fixed function, right out of the textbook implementation of some equations, turned into more of a little programmable block. And here, vertex shader and tessellation and geometry shader, we're sort of referring to what happened in that outer block on the left. And fragments or pixel shaders were the lower block on the with the lower block on the super block on the left. And so these fixed function things got enhanced to be more programmable, put a lot more creativity in the application programmer's hands, and you could get a lot better, different effects. You could evolve things. You could customize things to do, things that you wanted. Um, and that all turned out to be interesting. And again, if you were building a chip to implement this pipeline on the right, you could choose to put so much resources, so much chip area into the orange boxes on the upper part, or maybe you want to put more emphasis on the orange box on the bottom, and you could differentiate your product by how it performed. And maybe across the same product line at different price points, you would put different emphasis. So just as a caveat, as I put together this presentation, I went and searched slide decks from the last, 15 years. So I've grabbed a whole bunch of old slides that I'm repurposing for the purpose of the talk. So I hope you don't mind, but I found it interesting. So this timeline sort of depicts for me this progression toward programmability. On the very left side of the Riva 128 and Riva TNT, they were very typical fixed function pipelines. TNT added more emphasis in the texturing pipeline. Texturing is like a way of not just saying here's the color to put on an object, but here's a pointer to a map of colors. And that map could look like a decal, it could look like wood texture, it could look like, clouds, but it was sort of another way of getting color information into the device. But as we move forward and we got into the early 2000s, now we started that all that programmability started showing up. Those pipeline stages I'll show you in a minute turned into be little processors. Now they had an instruction set and a set of operands, inputs and outputs that matched the precision that was needed just for that stage. But they were little processors, had their own little instruction set, and the world was getting better. The imagery we were producing was getting better. Developers were, showing their creativity more and more, and it was an interesting time. But as we crossed over to the GeForce 3 family, at least in the Nvidia product line, that's when things got interesting, in that we took all those programmable stages and we instead implemented one programmable block, one processor. We called it a streaming multimedia processor that could do the calculations for any of those programmable stages. Now, by investing in that one block, you could actually increase your pixel processing performance or your triangle vertice processing performance, and the application could trade off how much time was spent on either. So you didn't have to make an upfront decision so much on how you spent your resources. And as you go forward, things got more and more programmable. The power of that processor increased, the number of those processors increased. Here's a slide that goes back a while. And the last Nvidia dot is the G70, and that's the GPU that we introduced that, first of all, coined the term GPU. I think that was the that was the device where excuse me, I should go back. GeForce 256 that I showed in the previous slide was where we first coined the term GPU, and it was given that moniker to recognize that at that point, once we added the mathematics to take vertices and off an object and convert them all in the chip, transform them onto the screen, that represented a full computer graphics pipeline. And now we had a full-fledged processor. But G70 was the processor where the stages got highly programmatic, the individual pipeline stages, as I mentioned. And if you noticed, as the green line goes up and to the right, it's a recognition that we started adding more and more resources to improve the performance of our device. And if you counted those resources in aggregate, you had a lot of performance. So let's just move forward. So this is the a pipeline diagram of the G70. So each of these blocks, there's a block at the top with how many? Looks like eight small blocks, and then there's 6 larger blocks partway down, and then however many on the very bottom. Each of those were a series of processors, and they had an instruction set to do whatever that stage required. And we chose in this part to put that much resources. We could have added more blocks in the middle if we wanted, or more blocks at the bottom, but we made our trade-off. And the trade-offs were being made to improve performance and to increase the quality of the imagery we're producing. So that was in 2005. Now, along the way, I had mentioned that graduate students had recognized that there was power in all this ability to do the mathematics of graphics, and students started taking these consumer devices that were readily available and reprogramming them to do something that they were interested in, to do their research. And it was an interesting time, because it was an interesting effort, and I applaud them, because we made them do absolute headstands. There was no way to program these chips unless what came in looked like triangles and graphical objects, and that you had colors and vertices, and that you had to, somehow fake math into doing whatever you want and get what was written out to be interpretable as whatever information you were trying to produce. But they did it. and they were getting some really remarkable results. So this wasn't lost on us. And one thing I'll say about Nvidia, and what we're really good at, is we like to say is picking the small signals out of the noise. So as we started understanding these other applications of our devices, and that difficult problems were solutions to difficult problems were being enhanced by the presence of our devices in the marketplace, we latched onto it. The two people on the right, on the lower, is Ian. Ian ended up writing a streaming language implementation on GPUs. Streaming is kind of the style of computation that GPUs do. You send a bunch of data from the top of the pipeline down through the bottom, and it flows through and goes into the frame buffer, into the memory. And so that turned out to be relevant. At the same time, we ended up attracting Ian to join us as a young grad student out of Stanford. The late John Nichols joined us, who was a seasoned industry veteran and a real expert in parallel computation. And these two guys helped NVIDIA map a new language and a new model of parallel computing onto the GPU structure that I showed you before. And this allowed the programming of our chip for more general purpose applications to not have to mimic graphics and remap your things to textures and triangles, but to program it in C or C++ or Fortran. And it made the accessibility of a parallel processor that much easier, which led to an unprecedented, I think, growth and proliferation of parallel programming and parallel processing. And so NVIDIA, and this is another one of these big aha moments that I'll give us full credit for, we decided to go in whole hog. This was a $0 billion opportunity at the time. A few grad students, doing their dissertations on cheap hardware they got down at the local electronic store. But we foresaw the opportunity or the potential to, one, increase our market size and breadth, but to allow our devices to solve some really interesting problems. So this is what we called the G80. And here was the first introduction of a unified processor. The streaming multimedia processors are these 8 things in the middle. The SPs we called streaming processors. Later, those SPs got named CUDA cores. But when this device was doing graphics, this is how the world would, or the programmer would see it. And these blocks in the middle would just, at one point be processing vertices, and next point doing something about texturing, and next point, a little while later do something about vertices or pixels or fragments. And you would just keep the processors operating on whatever the part of the pipeline your particular application had a lot of need for. If there was a lot of triangles, but very few pixels per triangle, then you'd want it to spend its time processing vertices. If there was very few triangles, but really large, you'd like, covering lots of pixels, then you'd have it spend more time on pixel processing, and you could dynamically vary that. So that was its graphics mode. And let me point out, by the way, the chip I showed you before, which was about a year and a half earlier in time, it was about 300 million transistors. So we went from 250,000 transistors on, doing Virtua Fighter to 30 million just prior to this generational upgrade. And this device was about 700 million transistors. Just to show you the amount of, investment in this stuff. So that was its graphics mode, but then you could also have it operated in compute mode, where all those processors and all those registers and caches and all that other stuff now got mappable to be accessible to this CUDA language without doing headstands and like I said, programmed out of C++, which is a very familiar environment. Now, it turns out, and this is another part of the story that I really liked remembering. This isn't just for solving a graduate student's thesis problems. Turns out, as graphics evolved, these processors running in this mode could do all the physics calculations, could influence and change how things got rendered. You could do collisions and deformations and interactions, and you could use it for light transportation, explosions, particle behavior. So this became an integral part of the graphics capabilities. Yet it also exposed this whole other face of the device. So this turned out to be a big juncture. And this another old slide I grabbed. This sort of shows the power of that decision we made to invent. The decision we actually took was to put the CUDA general purpose GPU calculation modes in every chip we made, whether it was aimed at a cell phone, an embedded device, or the highest end machines we could sell. Now, it took a few years before it showed up in every device, but that's what's made this the most prolific parallel processor in the world, because it's in everything, and our investment in it helps our core market, which is graphics. So you could see those things. CUDA was launched in 2006, 2007. GPUs started showing up in large systems. It ended up in national supercomputer labs. Big science started happening. And then as you get in the 2012 to 2014 time, that's when sort of the big bang of AI started. And I'll go through that more in a minute. But so you could see this progression. But once the device became generally programmable, all sorts of avenues opened up. So the big bang, as I was referring to, is a couple things happened. A researcher at the University of Toronto, Alex Krzyzewski, was able to win a contest by recognizing images, like a million examples of images, or we learned to recognize a million examples of images, and won a competition called ImageNet. Not long after, Andrew Yang at Stanford was able to figure out how to use GPUs to do some of this training. Prior to all this, the mathematics of a lot of the AI stuff was known. It was just too expensive to do. There wasn't enough data to help train these things. You couldn't have enough complexity. So a whole bunch of stuff came together at the same time. Microsoft and Google started commercializing some of this stuff, and we're able to get image recognition better than humans in some cases. Voice recognition, and started picking up on this approach to learning, and the quality of voice recognition was going up. All sorts of things started happening once the algorithms and the hardware and the techniques came together. On the bottom here was just layman's way of looking at how some of this image recognition stuff would start. But you would take a series of images, maybe in the first layer of a network, early layers of a network, you would pick off some key edges, and then in later things you would say, if there was enough of these edges in the right place, you might have this other sort of super composited structure. And if you had enough of that stuff as you went through the network, you might say, it's a boat. It's a lot of mathematics. It's a lot of data movement. But as it turns out, you're doing a lot of the same mathematics across a lot of the image. That's kind of like graphics. A lot of calculations, similar calculations done across a whole array of data. And that mapping wasn't missed on people, and it turns out it was a really good mapping. And so we enter the era of AI. This is not news to anybody. Things were always were done on the PC, and then the mobile and the cloud. I heard somebody describing some of the new a lot of the stuff that's happening in the virtual worlds as yet another screen. which is kind of interesting as you know, PC screen, mobile screen, virtual screens. The other point I would point out is that some have called the AI as kind of a revolution. And in some respects it is. So we now have basically automated automation. If you think about a machine learning, how to do a task, and then being able to do the task, you've kind of automated automation. And it's also another perspective is software writing software, which is a big deal. So AI clearly has influenced and is having impact on all sorts of industries, and I'm not going to spend the time wowing you with you know, application areas that have you know, been impressive, but I will spend a little bit of time on pointing out some of the places AI could be applied. Before doing that, I just here's a cartoonish thing that sort of shows what's going to happen. So what AI does is it takes learnings and generalizes them. So the learning part is what we call training. You give it a lot of experience. So the experience is going to have to be represented in data of some sort, whether it's images or cause and effects relationships, so your inventory levels, you know, weather patterns, whatever. You're going to take a lot of experience, apply it to a series of nodes that have mathematics associated with them that forward their results to another layer and another layer and another layer. And each of these nodes, as they take in input from the previous level, have weightings on those inputs. And when you get all the way to the end, there's an output, and the output could identify, does the network recognize, if you put one of those pictures, let's say it was a picture of a dog, at the end, does it say it's a dog? If it doesn't, then you go the other way and you start adjusting some of those weights at the inputs of some of those circles. And then you try it again, and you keep doing this forward backward process until the weights are adjusted such that all the training input comes in, gives you the correct output out on the right side. That's called the training mode. That is mathematically intensive. It is a real processing accomplishment when you get done with it. It takes a lot of data, takes a lot of horsepower to do. But when you're done, the network that results doesn't require typically as much horsepower to just use it. Now, when you're in using mode, we call it inference, you apply an input that maybe it's never seen, that's related to the training data, and it tells you, based on the experience it's captured from that training data, what it thinks the resulting thing is. And now you're using the AI network that was produced. So just a quick aside. So here, here's some of the one of the applications of AI we use to make computer graphics, to make better pictures. And this is a demo that our group did called Marbles. And I think it's a way of showing the quality of state-of-the-art computer graphics without having a game where things are being shot up. In the interest of time, I'm not going to let this play through, so let me just advance by it. But you get the sense there's all sorts of physically accurate things going on. The way the marble reflects and refracts, and the colors, and the wood surfaces, the physics, all that's being done on the GPU. Okay, so a little bit on how maybe some of the pretty imagery is done. One of the things that we've introduced lately that the computational horsepower of the device has allowed is ray tracing, real-time ray tracing. Ray tracing, I mentioned that most everything done in computer graphics has been a hack. Turns out ray tracing mimics the actual physics of the way light transport works and the way our eye sees things. So in ray tracing, you take imagine rays or arrows coming out of your eyes into the scene, and everywhere it looks, it either sees a color or bounces off of a light reflects or refracts, and eventually it makes it to the light source, and you could then say, okay, now I know the color of that pixel. Sort of lame explanation, but we take it's a very computationally expensive thing to do. So instead of doing it at the highest resolutions, we do it at a low resolution. We take some other information about the dynamic nature of the scene, and we train a network to predict basically what a higher resolution version of that image would be. And we train that network using supercomputers and a much higher resolution image as sort of the truth. So you make a prediction, you compare it against what a really super high resolution version of that image would be, you figure out what's different, you go back, you adjust the weights in the network, you try it again, and we do this loop. And by doing this and including those motion vectors, we're able to generalize. So if we train it on enough images, when it sees an image that is not this genre of game, not this style of image, it still makes a really good, better than other approach estimate of what that higher resolution image would be. And we get to not spend as many cycles generating that higher resolution image. And it turns out a big win. You get the look and marvels. Artificial intelligence clearly has affected a lot of industry and a lot of things. I'll just move right through this. Here's a little video about some of the work our researchers are doing to progress AI. And by doing this work, we inform our devices on how they need to evolve also to improve performance and capabilities. I hope this is coming across the Zoom.
我是第一财经的记者，我今天呢来为 Nvidia 录制这段视频，让大家看一下 Nvidia。
I know I'm running late, so I'm going to skip through this too. Sorry. One of the things that the GPU has been able to contribute to is the fight against COVID. There's some really dramatic simulations of the virus and of the spike proteins. This helped accelerate vaccines and treatments, and very proud of that. Here's just a series of slides just showing you some of the things where AI is and will be applied. If you're a drone looking over things, you want to recognize what you're seeing. These are all, each of these colors represent something that AI's trained networks are and will be used to identify. In a futuristic robot scene that we could all envision ourselves being in, think of what the robot has to do, is to understand what the people are talking about, recognize what they're asking for, understand the things it may have to interact with. And in the future, all sorts of things are going to be autonomous. And it doesn't have to be a robot, doesn't have to be a car. There'll just be a lot of autonomy, and AI is going to be essential to that. Here's a scene that, a smart city of the future, whether it's for safety or convenience. You'd want to recognize if something happened in the crowd that you need to send law enforcement. You may be able to head off some crime. You maybe identify lost things, find a lost child, get some statistics to help you plan your own growth. And I'm going to end with something that just happened in the last couple of weeks. The supercomputer that UF installed didn't power up till early January, and literally 2 months after this machine turned on, not only was it up and running and fully functional, it actually created history by creating the largest clinical language model or the best clinical language model ever devised, using UF Health's data of over 1 million patients. And basically, it took the transcribed doctor's notes, ingested it all, was able to I don't know what the word is, make it so no record is, nothing that was brought in was identifiable back to a given patient, but it was also then able to characterize these random doctors and nurses and clinicians' notes into something that was usable and accurate. And you can just envision it being used for all sorts of things. And this was just an amazing accomplishment. And it just shows you that with the right horsepower and the right people and the right data, great things are just around the corner. I started off that, we're creating things for the Da Vinci's of our time. It's been a long path. As I mentioned, Nvidia has chosen to make the compute capability available across all our devices, whether it's a thing on the right, the Jetson, which is like a Raspberry Pi processor type thing that can go into any small device to give it intelligence, all the way through supercomputers, and we're happy to sell people any part of this technology, from chips to boards to systems to supercomputers. And with that, I'm just going to end you with a quick video and give it back to Dr. Abernethy.
I am a creator. Blending art and technology. To immerse our senses. I am a healer, helping us take the next step and see what's possible.
Wow.
Can you really see?
Yes.
Oh, wow.
I am a pioneer, finding life-saving answers. And pushing the edge to the outer limits. I am a guardian, defending our oceans.
Roger that, fly by inbound.
And the magnificent creatures that call them home. I am a protector, helping the earth breathe easier. And watching over it for generations to come. I am a storyteller, giving emotion to words and bringing them to life. I am even the composer of the music. I am AI, brought to life by Nvidia, deep learning, and brilliant minds everywhere.
And with that, I thank you. And
Thank you so much, Chris. That was fascinating. We now have an opportunity to take questions from the audience, so please paste your questions in the chat function or in the Q&A box. Let's see. So I have several questions here from some of our attendees. This question is about the future of quantum computing at Nvidia. Any comments about how Nvidia might play a role in that field, Chris?
Well, the one, it's a field we watch closely. And when I was running research, I had a whole bunch of folks making sure we knew where it was going. The progress people are making in quantum computing is immense, enormous, and a little surprising, the pace of things. NVIDIA actually just released libraries to accelerate the modeling of quantum computing and qubits. So we are trying to enable the science and the innovation move forward as fast as we can. Will it be mainstream for use in your home? I doubt it. Will it have a place in data centers and large research facilities? I'm sure. When it happens, it's probably sooner than we think. I guess is all I can tell you. Not an expert in the area.
How involved is NVIDIA in edge computing in terms of either hardware development or research?
Well, we are big. We have whole product lines aimed at providing the capability to. So first of all, one of the principle may not be the right word. One of the predominant architectures for computing these days is this hybrid where some stuff's done in the cloud and some stuff's done on premise or at the point of data acquisition. I do think that model is going to continue, but for real-time response and accommodation of the circumstances, and I think doing a lot of computation at the edge is going to become more and more prevalent. So we have products that range from something you'd embed in a device, in a robot, to computers, large scale rack-mounted things that can do as much of the computation at the edge as you want. Turns out by pre-processing, by doing some computation at the edge, the bandwidth needed back to the central data center is much less, and the process can, the responsiveness of everything can be greatly enhanced. So I think there's going to be a lot. I mean, IoT, which is something UF is big into. There is just so much data being collected. The growth in sensors and smart devices that can monitor their environments is so great that doing something to pre-process all that data and make a response quickly without the latency, even if it's milliseconds, the latency could kill you, or could affect the outcome. So doing stuff at the edge, I think, is key. I think combining smart sensors and massive amount of sensors with edge computing capability is going to be predominant, the norm in a lot of applications.
What is your view of the future of chip feature size?
Well, it keeps getting smaller, doesn't it?
When does it stop?
I mean, the chip that's in the supercomputer that you guys just installed is 54 billion with a B transistors. Now, the first one I mentioned in the talk was 250,000. So that's my career, from 250,000, and that was like the biggest thing ever made at the time, to 54 billion, which I think is probably like the biggest thing ever made that wasn't just all memory. In the span of one person's career, you can't imagine where it's going from here. But every time there's a barrier, somebody climbs over it. So feature size seems to be getting smaller. The challenge to power it and cool it is ever increasing, which is has made computer science pretty interesting, and computer architecture and the system design around all these things. So keep putting out smart students, because we need them.
I would be willing to bet that they'll be hard pressed to match the giant leaps in technology that were made during the time of your career, Chris. But
well,
it'll be interesting to see what they come up with.
I think you'll be amazed. hey, when I got out of school, I remember thinking, well, I'm reading all the magazines and I'm trying to enter an industry, and I think, God, all the cool stuff's already been done. I'm just here to, sort of polish these things, not invent new ones. So, I thought it was all over back then. I'm sure when our, the graduating students today enter the field, they'll wow us. We won't even recognize.
I have a question for you, Chris. I'm really intrigued by the decision that you all made to pursue computational processing in addition to just graphics end products. Can you just give me a little bit of insight into what gave you the confidence, or most companies would have said, well, that's too different, that's too far away from what we do, that's not our core business. What made Nvidia different? What was it about your culture that allowed you to make that decision?
Yeah, I'll talk about it, but I can't really say I was responsible for the decision. So I'm relaying, how it went down among a few key people. But the, when there's a pragmatic side, there's a business side. Computer graphics was, it was a market that was healthy and growing, but not growing leaps and bounds. And, at some point you could envision good enough. Good enough is the impetus to progress, and we just didn't want that to happen. So we were always, so one, there's a business reason to expand your market footprint, to expand the breadth of the markets and services you can provide. So there's that. There's the other side, and this sort of comes down to I think the mindset of our executive staff, and my partner Jensen, and in that we should do, we had evolved into a very capable company. We were doing chip design at a level and scale that almost no one else was doing, and getting it right first time. We were doing hard things, and we kind of, I don't know whether it was a conscious decision or fell into it. We should focus on hard things. We should focus on things that we were uniquely capable of doing. Not that we could just do. We could build anything. We're a lot of capable people, but we chose not to. We chose to do computer graphics better than anybody. And we chose to tackle hard problems and make them, throw the company at it. And the problems that involve the whole company turned out to be quite sticky. It's hard to replicate something that takes 20 disciplines working together, because most companies aren't organized in a way that allows that. And we were. So we sort of fell into, and it's a philosophy that guides us for ever since. We should do things we're uniquely capable of doing that others won't do, or others couldn't do. And we should do things that, if we should succeed, will be impactful. And, our GPUs have a day job. We were being well subsidized by your kids, my kids, and that wasn't going away. And the thing I pointed out that I also found is kind of a nice aha moment when I replayed the history. All these investments we were making, 90% of them helped our core market, helped keep the lights on. Others that were building, just a supercomputer chip, or just they have to succeed in the new market to have funding to keep going. We were succeeding in an adjacent market, which allowed almost all our investment to be divvied out, to be useful, to be beneficial to the whole. So I think, those combinations. And the other thing is, we built Nvidia around trying to find the best, smartest people and giving them a place to do their life's work. This was inspiring. As we started doing more than just gaming, I think it energized everybody. And it turned out to be a good move, I think.
So along those lines, there have been a few questions from students or people involved in recruiting students. What are your recommendations for getting started with AI for a student that has no experience in the field?
Well, one, go to UF.
Great answer,
You're
Chris.
going to make AI available across the curriculum.
That's right.
There's lots of resources. Nvidia just had our big yearly conference, and it was free, and you could take classes and courses and tutorials to your heart's content. Every one of the online universities and providers have information available. I think if you want to learn about it, it's available. And I think it's going to be a key part of it, just like you guys have decided, it's going to be a key part of a competitive employees toolkit resume moving forward, because I think it's not going to be that pervasive.
On the flip side of this, Chris, there are the employers who are trying to find people with these kind of skills. This question asks, with the challenging nature of recruiting for new employees, have you been involved or know people in your field of AI that are tackling this issue?
Well, it's first of all, we need more people trained. We need to understand the skill sets that they come out with as an employer, so you know how to hire. While there's few, then I imagine the big guys or the more prestigious, the more visible employers win. But when this becomes a pervasive skill, then this will be a lot easier to hire for. The government's under the same, as you know, trying to find skilled people to work at the national issues. And AI is certainly a national competitiveness issue, if not a security issue. So there's a lot of people working on this, and there's recent reports from the National Security Council on AI, and had all sorts of recommendations. Employers want to find more people. Provider of employees, like universities, are trying to provide more people. We need the students to step in and be those people.
Unfortunately, in the interest of time, this next question will have to be our last one, Chris. What are the best opportunities available for small businesses to collaborate with Nvidia?
Well, now there's a good question that I don't actually know the answer to, because I don't really know all the pathways into the company. I would imagine, send us notes, send us an inquiry. There's salespeople all over. We have representatives, all over. I would try to engage with it. I can't answer that because it's not a part of the company I've run or know much about. But we want to meet up. We have a startup group that invests in startups and interesting technologies. Gentleman runs is Jeff Herbst. I'm sure there's plenty of ways to get into us. I would try whichever way. Send me a note. I'd be happy to forward it.
Great. You just got your invitation there, folks. Well, Chris, there's more questions. We could spend all day chatting with you, but unfortunately we're out of time. So we'll have to conclude today's presentation. But again, I just want to thank you for a terrific webinar. And I want to thank all of the attendees for participating today. We'll be hosting another webinar next month, and we'll be in touch with those details soon. Thank you so much for joining us today. And as always, go Gators.
Go Gators. Thank you.